Hi, everybody. I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering, and you are here for addressing challenges in software-defined systems electronic development. If that's not what you're here for, you're in the wrong room. Discussion today on the left here is Matthew Corbett, is Principal Technical Fellow at Collins Aerospace. We have Suraj Gajendra, Vice President of Automotive Products for Software and Solutions at ARM. Alex Starr, Corporate Fellow at AMD. And David Fritz, Vice President of Hybrid Physical and Virtual Systems at Siemens EDA. So I'm going to grab a seat here. To the panel, how does software-defined differ from a hardware-software co-design? Why don't we start going down the list here? Matthew?
I'd say for me, it's the difference between thinking about your system problem in a software context, a software first methodology, versus more of the hardware co-design being more of how do you integrate software and hardware together earlier as a shift left type of approach.
Yeah, I think the way we look at it is it's more about enabling an infrastructure when it comes to automotive primarily or any other market. It's more about enabling a software infrastructure that can drive pushing software updates and new feature upgrades and stuff like that even after the vehicle rolls out of the dealership, right? So building that infrastructure in the cloud and in the car, that entire aspect is what software defined really means. But at the same time, when it comes to software hardware co-design, the fundamental aim for that is to ensure that the hardware that is being developed is aware of what software application that it needs to run. So there is a lot more to the purpose build. At the same time, you also have when the first hardware comes back from the factory and stuff, you are rest assured that okay, because you understood and you know what kind of software needs to run on it, you basically sort of are in a position to then feel easy about it, and then it's all about development from that point onwards.
Alex, how does this actually change what you're doing?
Yeah, so I think, we've been in an era of you design the hardware first and then you write software for it. And, that's done us very well for a long time. But as we're seeing, new techniques coming out, architectures changing from a software perspective particularly, I think that is creating more flexibility, and that hardware needs to adapt and become more flexible. And so I think it's ultimately some kind of trade-off between how much bespoke hardware do you have, how flexible is that, how flexible is your software. And I think we're in this place now where we're turning the dial a little more towards the software side to create deliberately more flexibility. And that creates challenges, of course, economically and everything. But I think that's generally how we see things. So going more to a software first approach.
And David, from the EDA side, what's actually changed here? Is this really different from hardware software co-design, or is it still the same process?
Well, I think hardware software co-design is a part of being software designed, but it's based on technology that's 15, sometimes 20 years old that prevented us from moving forward to have a real pure software perspective on systems. So I see software-defined products, software-defined systems as several things that are different. Number one, the software has to be able to impact the hardware, and hardware needs to have an impact on the software. It's that codependency that you need to exploit if you really want to have a differentiated product out there. So as was alluded before by the other panelists, there is a whole infrastructure that needs to be built around the hardware and the software team to enable that. One of the key points there is how do you actually validate that you're headed towards a solution that's going to meet your requirements down the road. No longer can we, do this via spreadsheet or something like that, or just do iteration, generation after generation. It all has to be designed to purpose, as you heard, but the infrastructure to do that and the tools behind it are very different, much more advanced than they were 10 or 15 years ago.
And just want to add one thing, Ed, there. I think it's more about, at the same time, the complexity in a segment like automotive or robotics or aerospace is significantly more than a cell phone or a laptop, right? So the tools have to sort of think about all of those challenges in terms of, okay, what happens when mixed criticality workloads or mixed criticality software comes into play in a software defined environment versus just running plain general purpose applications. So there is a lot of challenges and a lot of aspects that needs to be thought through as well.
Alex, how does this affect what you're developing in terms of software? You've got to prototype this based upon the hardware, but the hardware doesn't exist yet, and now you're starting to say, okay, we're going to define it from the software.
Yeah, always a problem. So we do tons of pre-silicon validation, of course, and using emulation, virtual platforms, and so on to model these systems. And so as that software adapts, we're always creating these virtual models of the design ahead of time, and that enables you to do these kind of what-if type analysis of what if the software was like this? Does it work? Does the design actually meet its requirements, and so on? And I think that gives us doors as well into increasing the flexibility of what the hardware can achieve versus the sort of rapidly developing algorithms that we see out there, especially with AI kind of being introduced into many products and adapting very fast. You have to avoid the trap of having very bespoke hardware that's focused on one thing when it might change in the next week. So that kind of pre-silicon enablement is super key for enabling this software-defined.
Can I extend a little bit on the what if scenario? That's really critical. We all know that over time electronic systems degrade in performance. And when we're talking about automotive and aerospace and defense and things like that, these are very long lifespans. So there's definitely going to be a change during the process of using one of these systems. So having the ability to test those scenarios about the degradation, additional latency that gets added, all kinds of arbitration that now may happen, it didn't happen before, or the target frequency can't be reached, all kinds of things could happen. But having an SDV environment or a software-defined product environment to define that and explore those possibilities up front is really a game changer for all of these industries.
And Matthew, you're obviously working in an industry where if something goes wrong, you've got big problems.
Absolutely. And, understanding the coupling between the software, when you think about how you want to define different workloads, define different functions, we talk about different criticalities of functionality, understanding the coupling and understanding that it's not going to change the deterministic behavior of your real-time system is very, very key in a software-defined environment.
Yeah, and just wanted to add a point back to what David said. Again, if you think about where some of us are in the whole supply chain, so ARM sits at the forefront because we develop some of the compute IPs that then gets put into computers that partners like AMD basically go build SoCs, and that then goes into devices, and that then goes into vehicles, right? So most of the time we work on IPs, we build compute IPs that will eventually go into a car 5 years later. So, looking into all of the qualification, of course, I'm not counting the China time here. I'm just counting the traditional time. But that's the timeline. So it becomes so much more important for us to understand, again, I would be a fool to basically say, oh, I absolutely know what that workload is going to be 5 years down the lane. We can't even predict what's happening 6 months down the lane, as from an AI perspective these days. So it becomes so much important, right? We try and in partnership with partners like Siemens and others, we try and ensure that we model as much as the system as possible as early as possible, and then run as much as software on that model as possible, so that we sort of plan ahead and keep that going in terms of meeting the actual requirements. So it's never easy, but we have to work as a team. We have to work as a there has to be a lot of collaboration, ecosystem collaboration, to try and enable things like this.
It's also not like flicking a switch, though, where you turn it on an automobile or a jet plane or a rocket, because this stuff still has to be tested. It still has to work with the silicon. It still goes through this multi-year process. So how much can you actually shave off the time here?
It's pretty dramatic. It's pretty dramatic. Actually, if you've seen the Pay 360 car out there, that's one of the things we're trying to demonstrate with that. That you can run these scenarios in the virtual world and have enough fidelity that you gain confidence in them. And you gain that confidence by correlating what's happening virtually in the cloud with something that's physical. So in a case of software-defined vehicle, the whole idea is you develop the hardware, you develop the software virtually. Once the hardware is available, the same software runs on the hardware, and you put it on the track and you start testing. Savings millions and millions and millions of driving miles, an incredible number of terabytes of redundant data that need to be filtered through.
Yeah, I want to add to that. It enables you to create these solutions that you wouldn't otherwise be able to make at all, because you can iterate pre-silicon in this environment to define, hey, what if we designed it like this? Oh no, that doesn't work. Let's try it like this. And if you're looking at the rapid change, especially in automotive, from very distinct ECUs that are all sort of isolated from each other and moving to more centralized compute, then suddenly you're only really able to make that big leap and quickly enough to really accelerate the market by having these pre-silicon solutions. Otherwise, you're just building stuff and hoping it works, and then it doesn't, and the loop is too long. So I think it's a fundamental shift of being able to enable software-defined approaches is that kind of capability that David mentioned.
Yeah, I'll give you a little bit of example just to add to what they said. I think so. ARM. So we've been supplying automotive enhanced IPs into the automotive space every 3 years. 2018 was the first one. 2021 was the next wave. 2024 was the next wave. The IPs that we actually launched in early part of 2021 became available in a chip on a platform, in a developer platform for the software ecosystem end of 2022. So there was 18 months of lag between when we actually put the IPs on the shelf and when it eventually became available for software developers. I'm not going to name which chip is that, but it's end of 2022. And that wasn't a great chip for software development. Okay. Now, what we did in 2024, again, together with David and others, is on the day of our IP launch, we basically had virtual platforms and virtual models for software development on that day zero. On March 13th, 2024, we basically launched our 2024 generation of IPs, and we basically had Siemens virtual platforms on that day, right? What did that do is basically that enabled all of the software development ecosystem partners to start developing their software as when our IPs became available. That was the time savings that we could actually achieve, right? Of course, you're absolutely right. We'll have to go redo, validate, and when the silicon comes back, when the board comes back and all of that stuff. But fundamentally, enabling that infrastructure as early as possible is key. How much we can actually achieve depends on the application, depends on the rest of the infrastructure.
I think another key point on enablement in early development is the costs of devices are becoming more and more expensive, and the cost to do a respin is becoming very expensive as well. So having the ability to have these virtual environments, virtual platforms, and prove out your workloads, prove out your software ahead of real hardware, and use those workloads to actually sign off your hardware of your tape out is important as well, and that can't be understated.
Forgive me, but I think these guys have started building a really important case that I kind of want to put the icing on the cake there. The number one thing is, imagine you buy ARM IP. It can be configured any number of ways. You need to decide as a designer how it should be configured such that it runs a particular workload from a customer you don't yet have well. There are all kinds of unknowns. In the past, you would eliminate those unknowns one at a time. In a software-defined system, however, you can take the models of the ARM IP, you can configure them in any different number of ways. You can put realistic workloads on those and find out the ideal configuration for your target market the first time. We talk about respins because of front-end, back-end, place and route errors, things like that. Mean time between failure issues, okay, those are real. But the original mistake happens long before you even start the implementation process by choosing the wrong number of cores, the wrong cache sizes, okay, the wrong number of clusters, the wrong cores themselves. So the macro problems you find early using this methodology. And that's one of the key benefits.
So let's follow up on that, because when we look at a lot of the proponents of software-defined, it's billed as an approach to future-proofing. So how does this affect the lifespan of these devices? Are they better? Are they worse? You're basically building some flexibility into the hardware to allow for the software changes, but what's the impact of that?
I think the first thing to consider is, how do you provision, for your future workloads? It's been talked about how hard that is to define what your workload is going to be 10 years down the road. But understanding what kind of programmable accelerators that make sense for your architectures, whether from I/O acceleration or some other AI type of acceleration architecture, is what's really important to try to understand.
So just to add to that, I think so allowing software upgradability on existing hardware, yes, it does sort of increase the lifespan. It doesn't, of a given hardware, so which is good. But at the same time, it also builds stickiness to that hardware platform, right? For example, generation over generation, the amount of heavy lift that particular OEM has to do. So let's just say, a specific car OEM basically loads up their car with a lot of software features, and then that keeps happening over, every quarter or something like that. Now, when they are ready to go migrate into the next generation, there's a lot of stickiness that's built from a hardware platform perspective and the software environment perspective. So yes, it does sort of, reduce the frequency of new devices, but at the same time, it builds stickiness to the component suppliers. It reduces a lot of redundant work that needs to be done generation over generation.
And you're still building the same kind of monitors into the hardware that you always did too, right? You can still have some visibility into how this thing is behaving over time, in addition to the ability to change the software as you go for different features.
Yeah, that's right. We stream data off these systems as they're running and collect that, in the lab and in real time out in the field, to really understand how things are being used. But also we do it pre-silicon and understand that same data pre-silicon as much as we can. And that really helps define, how the system should be used. Are they being used in the right way? Can we give guidance to software engineers to re-architect things or just move things around a bit to make it run more smoothly in the field? So that telemetry data is coming back to us, and we're able to tweak as we go along. So that's a key part of extending the life, to your point before. So yeah.
David, how do you verify these systems as you go too? Because you've got a lot of changes that are almost ongoing, right?
Yeah, and that's part of the infrastructure that we talked about before. So the idea is you implement a full CI/CD, CV flow, okay, continuous integration, continuous deployment, continuous validation. One thing that's different about a software-defined product over a traditional approach is that you do unit testing like you've always done before. You do verification with emulation and simulation like you've always done before. But on top of that is a system-level approach to putting realistic data into that system pre-silicon and looking at the outputs that come out. Okay, so the whole concept is the Pay 360 car out here in the booth. That is running one scenario. That scenario was created partially automatically, partially with AI, partially manually driven. So in a system development environment, there's a whole new level of system level testing that happens, and you abstract that up to the human level. You don't worry about input vectors. You worry about that car's driving 100 kilometers an hour at night in the rain and something steps out in the road. Do you stop? So there's a whole class of system level verification that collects those to drive the stimulus into the rest of the system. So you have realistic stimulus in, you can do power and performance analysis from there. And in the absence of that realistic workload and realistic stimulus, it's just a bunch of guesses. So that's another thing that's very different about a software-defined product. And we're seeing that picked up in just about every industry that we go to, new teams that are developing this new way of system-level testing and validation. Assuming, of course, that there is a way to compare your results against the requirements that are defined at the system level and below.
So things are moving at an incredible pace here. You think about ChatGPT, which is less than 18 months old, right? Or somewhere in that neighborhood. That wasn't on anybody's horizon going back. How does that start? Can we, with these architectures for software defined, can we keep up with that? Is it starting to accelerate to the point where you really don't know what you're going to be defining the software?
Yeah, I mean, certainly the developments in AI are moving so fast that we don't know what's going to happen next week. But one of the approaches certainly AMD is taking is in our AI strategies is we've got general purpose AI compute solutions. We also have very bespoke edge inference solutions like Michaela at the keynote this morning was describing. And the combination of those two things helps us safeguard against how much things are going to change. So particularly software-defined kind of vehicles and those kind of approaches, this more general-based AI acceleration is going to be able to have longer legs and extend further into the future. But that being said, there's always a faster AI sort of general-purpose AI thing that's going to come out in a year's time. So yes, in theory it does, and it certainly is a strong strategy to do that. But ultimately, everybody's faced with the same challenge of the rate of change of just the industry and the AI algorithms, and we always want more compute. And can we do the same compute for less power in a much smaller solution? All of these sort of economics come into play for this future. So I think it's not as obvious as it might seem, but I think that's why our jobs are fun and interesting.
Yeah, I think so. At ARM last month, we did a compute subsystem launch, and we started talking about AI-defined vehicles. Okay, so what the narrative that we've been thinking about that is all the applications, some of the fundamental applications are being now transformed, driven by LLM models than traditional algorithms, right? So the applications are being rescoped based on what AI can actually do. For example, the classic example is the replacement of a user manual in a car, right? So instead of the 500-page booklet that you have in your glove box, it's going to be replaced by a voice assistant, and you basically talk to your car and say, okay, what's that indicator or what's this indicator, right? So now the applications are evolving, but at the same time, going back to the infrastructure that we talked about, that's fundamental, that's foundational. So the whole software-defined vehicle infrastructure that we have to build from cloud to car has to be there, and the AI applications will have to make use of that and run with it. So another, the whole idea of you have a new AI application, can you then bring that into the pre-silicon software environment? And then look, I mean, not every AI application needs needs to run 100% on an NPU or an AI accelerator. There's parts of it that can actually run on the CPU, parts of that just runs on the GPU and all that stuff. The decision of how much and how optimized that workload can actually run, those decisions can be made way ahead in the game, and you don't have to wait for the real hardware to show up. So that basically helps this whole development cycle, even from an AI application perspective.
One thing, interesting dimension I want to add, which touches on everything that's been said, is we're doing this pre-silicon work on these platforms, and so we're building data centers full of compute, CPU, GPU, AI accelerator compute that can run these models of the new product that's being software defined. And so you have to be able to map your software defined product onto that server grade hardware in a data center in order to drive your car 1 million miles before you actually do anything real with it. And so there's an interesting compatibility kind of angle there, and flexibility, meaning you want to be able to take that software that you're running for your product, the architecture of the software, have silicon that's you're designing that's going to be focused on that, but be able to take that exact workload and run it in an accelerated form in a data center on hardware that can accelerate it. And I think this is a very interesting sort of challenge that we're going through, especially in the automotive market. We've sort of been there in the sort of server x86 market for a while because the computes that are out there in the world, they're all basically x86 computes in these big data centers. So we've sort of been doing this native execution kind of capabilities today with, for many years with x86. Now we're seeing that coming along with ARM and inference engines as well, because you need to be able to run those inference workloads fast enough, not in a simulated manner. You actually have to run them at speed in order to be able to run the real scenarios of these software-defined products.
So now you're adding backward compatibility and standards into this, right? Because you really have to be able to say, okay, if we develop new software for this because it's based upon this, that's the whole idea behind this, it still has to be backward compatible with whatever's there. This could slow the whole process down, right?
Yeah. Yes. Let me start. So I think no, absolutely. I mean, that again, standardization can be achieved at different levels. One is at foundational software. Yes, absolutely. You will have to go build the foundational software based on standards, and I'll give you a couple of examples on that one. And then even at the middleware level, you have to at different levels of the middleware, you will have to push the right amount of standardization. Yes, there has to be scope for differentiations and application specific software and all that stuff. But at the same time, you will have to have the interoperability of some of those layers have to be standardized. Now, pulling that into the virtual platforms and virtual enablement that we're talking about, it adds so much benefit, as I mentioned earlier, right? So when you sort of think about one generation of hardware to the next generation of hardware, and if you basically build enough standardization in your software stack, there's so much reusability of that software stack going from one first generation to second generation. So it not only adds reusability, but it also sort of saves a lot of effort and cost. So, what we believe is standardization is a must-have at the right layers, at the right components. And at the same time, we also have to sort of ensure that, the optimization parts of it at wherever it actually is needed is also sort of preserved.
Yeah, I want to add something to that. So traditionally, the software and hardware are considered bonded together. One thing that's very different in a software-defined system is they are disjoint, but they leverage each other. So automotive is a great example, right? You would buy an ECU, the hardware is fixed to the software, and you deliver it as an integrated package. What's happening now, partly thanks to ARM SOFI, is we're shifting to a service-oriented architecture. So the software architecture is designed for that level of flexibility, to map different components to different pieces of hardware, to adjust to the hardware changing dynamically over time, and to adjust to software features being added on the fly, even over-the-air updates. Think about that for a minute. What we're saying is, if you did an over-the-air update to an architecture that isn't designed to handle that, you could easily violate a requirement that wasn't a problem before you did the update. And how do you find that? Okay, and a service-oriented architecture means in that simulation environment, I can help you find that type of problems before it all gets distributed out to the fleet. Okay, so that's a key difference there, and that can't happen without the infrastructure there, okay, with the understanding of the hardware can change early in the process, then becomes fixed, and then the software remains flexible.
So you're building the margin into the software instead of the hardware, right?
That's one way to look at it, yeah.
Matthew, what does this mean in terms of you obviously have to follow more standards than almost any other group here because the safety critical nature of your business. What's the impact of all these changes and basically trying to set the software up so that you can upgrade it over time?
Yeah, so thinking about it ahead of time, obviously, can you provide those updates over the air are you provisioned to make sure that you have good security infrastructure for making sure those updates are valid to be loaded into the system and installed into the system, especially when you're thinking about multi-DAL design assurance levels in my aerospace world, criticalities that are running on these platforms, how they interact with each other, how they, in a multi-core environment, and how they share resources. That always has an impact on the timing, making sure that we can detect those types of events and have infrastructure in place to ensure that in real-time deterministic behavior is always maintained.
Does it make it simpler to secure these devices because you can make the changes that faster?
Simpler? I don't know that it makes it simpler. Security is an evolving world out there. Being able to react to security threats and vulnerabilities is the most important thing, which is the thing that is enabled by these software-enabled systems.
Yeah, I think it also, again, knowing about the security requirements of those workloads as early as possible is also going to help how we're going to design the hardware, right? Because sometimes, if you don't have visibility into what those security requirements are, or just understanding how mixed critical systems really operate. I mean, there's one application that can be really, really highly secure, and the other one not so much. But the interoperability of how they're going to together run on a hardware platform is something that needs to be understood. So again, going back to enabling this infrastructure does give the developers the ability to say, okay, here's my critical security requirements for my applications. This is how I'm going to now, here are the features that's available to me on the hardware, way early in the game, and this is how I'm going to partition it depending on, and this is not just the hardware level, but also at the middle layers of software and the foundational software layers, and say, okay, here is how I'm going to partition, this is how I'm going to slice the whole system, this is where I'm going to run my secure workloads, and this is where I'm going to basically run the other workloads. I think it adds that, knowing that and getting that visibility definitely adds a lot more value in how we design the system.
Alex, you obviously have to work with a lot of security as well in your designs. What does the software defined do for you versus the way you traditionally did it?
Well, I think there's two components to that. There's the sort of the security into sort of new types of IPs and products that are maybe more on the edge, and that's one angle. The other piece is the virtualization angle, where software-defined vehicle, you're going to have components that are going to run in secure environments that are isolated from each other and protected security-wise. And so from an AMD perspective, we've been doing this for a long time with our server products, having very secure virtualization schemes and nested virtualization to be able to run multiple workloads in very secure manners with very high levels of security for banking and so on. In that piece of it doesn't really change, I don't think. I think we've got some good technology there. But I think it's, as we evolve and there's new components coming into the system, we've got to ensure the security of all of those pieces. And that's always an ongoing, challenge. There's always this, trade-off of how fast you can get something out versus how fast you can make it really secure. And so I think, we just live on that spectrum of where we're at.
And David, from your perspective, when you're developing a chip design, a lot of this has been, the big push has been push everything shift left as far as you go, concurrently design all the stuff. What changes here from a security standpoint when you're designing a chip with software versus the software first versus the hardware, and the software is defining how that's going to be used?
Well, engineers have a propensity for breaking things down into the smallest units and tackling them one at a time. Those days are over, right? Safety and security can't be an afterthought anymore. It needs to be a part of what you're designing from the very beginning. And, as Matt was saying earlier, and Alex as well. So the point is, if you think about this ahead of time, you know what the safety security requirements are, then as you're iterating through this process, those requirements are being verified on a daily basis. Just like any other requirement that could be a higher level. But safety and security and intrusion detection and response is a part from the very beginning, not an afterthought.
Let me. I'll give you a real world example on this one, without telling which car I drive or without putting any specific OEM under the under the bus here. So
Please give me content.
no, you'll figure it out as soon as I say the story. I live in London, and so my car OEM basically sent me an app notification saying, hey, you can actually, and for people who live in London, there's all the parking apps and automatic payments and stuff like that. So I got this notification saying, hey, you don't have to use your phone to make parking payments. Your car will basically know exactly where it is, what is the location code, and it can basically pay for itself. And if you're coming in late, you just, extend it based on this app thing. So I said, okay, cool. I mean, I don't have to sort of go looking for locations. It's all in the car. It's super. It's been about 8 months and I've still not gotten it working, right? And the error that I get is the hardware, the vehicle hardware and the system software doesn't meet the security standards to actually pin a credit card information and enable this feature. So I'm like, okay, there you go, right? So if the system designer would actually, I mean, if that was built with all of these workload requirements of awareness as early as possible, then you would be able to sort of, you don't have to get into situations like this.
Well, we're constantly updating our phones. If we start running into these problems where you're doing this in your vehicle, that's going to be a whole different type of environment, right? Everybody's going to be looking at this going, why did we go with this? So how do we minimize that? This is all the software defined, but the software definition varies from one application to the next. It varies from one circuit to the next. And as you start getting into these multi-die types of systems, it's a completely different world.
Yes, it's not easy. As what Alex was saying earlier, I mean, there's one aspect of newer applications and the challenges, and at the same time, there is another aspect of consolidation of E&E architecture in the car, right? So now, in traditionally the way some of these challenges with respect to mixed criticality and real-time requirements were solved with distributed systems. It's like, okay, I'm going to put a microcontroller there for this specific real-time operation. I'm going to put another safety MCU here for some other application. So it was all distributed. But the distributed architecture is not going to survive, because when you're talking about software defined, you will have to have software managed systems, and you can't basically have hundreds of computers in the car, all of them needing all sorts of software updates, right? It's not possible. So on one side, you have this consolidation of architecture, absolutely must have, but at the same time, you have these applications that have mixed criticality requirements. So I wouldn't say that we don't know how to enable this. There are different architectural aspects that are being defined, and how you can sort of partition out the workloads in terms of still effectively run it. There are some applications that do have to sit outside. There are some applications that all can be consolidated. So I think the industry, the ecosystem is together working on trying to define what that is, and then take one step at a time.
I just want to add one thing to that. The reason why this is becoming a very big issue is because whether it's automotive, aerospace, or whatever, there are new business models that need to be brought into play because of competition, particularly from overseas. So you can't compete on the number of cup holders anymore. You have to compete on the features that you're developing based on the requirements actually coming from your potential customer base. So Suraj's example was a really good one. Okay, there was a new feature they thought would differentiate that particular vehicle. So they didn't think about that particular feature in the context of the vehicle. And I'm trying to say there are so many companies out there who are trying to find that new business model and making some very significant errors on the way. We want to build our own operating system. We don't want to use Apple Play. We're going to develop our own from scratch. I mean, the list goes on and on and on. And there are a lot of scars out there. But the point of this panel is, if you modeled all that in advance, you had those requirements coming from whoever was defining your business model. That was a part of the design process from the beginning. All these things are very feasible. Adding them after the fact, not so much.
Well, I do think you might have a whole new level of road rage inside the cabin as opposed to outside. However, as you go forward here, what do you see as the opportunities? Let's think positive here. So what can we do that we couldn't do before? Matthew.
From aerospace perspective, we can add new capabilities to our platforms, offering new safety enhanced features to our avionics platforms that don't require us to go out to the airplane and pull the box or replace or reload the software. These are things that we could actually start pushing to the architecture.
I think there's actually a very exciting opportunity to do a lot of change and do things differently. And I think we'll see a dramatic shift in what's available and new features and capabilities because we can take these bigger steps forward by doing all the pre-silicon modeling that couldn't really be done before. So that's going to just enable and unlock a whole new wave of development, I think.
Yeah, I mean, adding to the new features and new capabilities, it's also, we believe that the software-defined vehicle infrastructure is also going to help us solve more complex problems more easily, like, autonomous driving, for example, high levels of ADAS, exactly the consolidation of IVI and ADAS in a common computer and stuff like that, because the infrastructure will enable us to sort of uncover the macro problems, as what David was saying earlier, as soon as possible. Then we can sort of, enable the transition, enable the newer capabilities from that standpoint as well.
Yeah, I think this is sort of the emergence of system level modeling, right? And it's something that we've sort of thought about in general as an industry in the past and known, that's a thing. But now these systems are getting unbelievably complicated. The vehicles, for example, very complicated. The AI deployment, data centers, it's thousands, millions of nodes operating as one entity with one piece of software running on it. That's a massive systemic complexity problem. And so I think now we're seeing these capabilities, and Pave 360 is an example of a digital twin kind of capability of being able to model systems, which is absolutely fundamental to how we go and develop these new products going forwards.
And when you're thinking of system, you're thinking potentially not just at data centers, potentially how it fits into the power grid too, right? We're talking very big integration of multiple systems.
Yeah, that's right. I mean, ultimately, that's right. You've got to go and build these data centers and deploy them in places where you have power. And yeah, ultimately, especially with the AI kind of world and how fast that's expanding, energy is going to be a problem. And so getting lower power compute, both in AI compute and general purpose compute, is fundamental to where this is all going for sure.
There's been a lot of discussion here about pre-silicon and modeling and things like that, ignoring the fact that a whole new set of technologies had to be developed to allow all that to happen. Okay, so using technology from the old co-ware days where, co-development just doesn't apply. I mean, your simulations would run in weeks or months, and we need them to run real time because we're running millions of them now to find all those corner cases. So that's another opportunity that is really, it is a new technology that has recently been developed that makes all this possible.
Matthew, where do you see this going for aerospace? I mean, how does this change things, in a significant way?
The most significant way that we've seen this changing our development is our ability to actually start, working on software, developing new approaches to system architectures ahead of, obviously ahead of the real silicon becoming available. This is helping us understand how we might want to partition our architectures a little bit differently, how we want to rebalance our workloads differently, and actually driving change into our software architectures because of the opportunity to save power in certain areas.
Do we need a different skill set to make all this work? Is it the same skills, or do we have to hire completely different people with different
Depends
training?
on the industry. Okay. I mean, what we're talking about now in smartphones and mobility, it's been there for a long time, right? Agile methodologies are an important part of utilizing the infrastructure that we're talking about. We're finding more and more automotive companies, as an example, adopting those modern software development methodologies, but it's by no means comprehensive yet. So yes, in some industries, there's a skill set change coming to take advantage of this.
Yeah, and I think, I don't see drastic change on new skill set, but at the same time, cross-pollination of those skill sets across companies is pretty critical. I'll give you an example. we just hired a couple of people who actually sort of, have 15, 20 years of experience in vehicle level modeling and, ECU level modeling, right? ARM had never thought about doing something like this if we were not so serious about investing in the whole shift left and software development, vehicle infrastructure development. So it's just us, for example, as an IP supplier thinking about the vehicle level modeling, what sort of, how would that going to then translate into what we have to do, work with partners like Siemens is that's going to change, right? You will see, I'm pretty sure Siemens also have something similar going on where they hire more people who have vehicle level experiences and stuff like that. I think that sort of cross pollination of skill sets is definitely something that we will see going forward.
Alex, you were about to say something.
Yeah, yes. I was going to say, similar to these guys mentioned, that the cross-pollination is definitely happening. We see it particularly internally between our software team and our hardware team. The style of approaches and the way we have to start looking at things from a hardware perspective for, the systemic, integration, the AI capabilities and how fast that's moving. Our own internal infrastructures and the hardware have to change how we do things, and that means that we need to get more onto these sort of continuous integration, continuous deployment, validation kind of cycles, which we sort of do. I think as a general industry, the hardware industry sort of does this, but I think now that software-based approach is coming in much stronger than it used to, and I think that we're getting good alignment across the two different disciplines now.
Our industry has been largely built on standards. Where do the standards come in now? Is it in the hardware? Is it in the software? Or is it in some combination of both? Because that's really the fastest way to get products to market, regardless of how you're doing things.
I think you'll see some natural sort of boundaries about where the hardware boundaries are going to be and what those interfaces are. Particularly given that typically it's chiplet based or multi-package based solutions now. They're going to be high-speed SerDes links. They'll have some kind of standard like UCIe or whatever. And so I think the hardware will have that. And I think naturally the software is going to sort of fit into that as well for a couple of reasons. One, because naturally when you have another accelerator, let's say, attached to a system, it's going to be in that other chiplet. So naturally there's a software that can run there and another one that can run the other chiplet. But I think also just from how do you verify and validate these things pre-silicon? You have to create a modular architecture where you can say, I can't have a piece of software that's going to be distributed across 20 different chiplets and be able to verify that all as one big, group of stuff. That's a difficult job. If you can have those software components match, physical IPs, then that allows you to do hardware software co-verification right within that one node and get much higher quality for that node, so that when you do bring these all together, you're in a better situation.
I want to add something to that. So the assumption has been so far in this discussion that you can get all the way down into the silicon to have that flexibility that we talked about in pre-silicon. Not all companies are ready to take that leap, particularly in automotive, okay? Their unit volume is not incredibly huge. So they have to be concerned about that. This whole concept of chiplets as a way of just focusing on packaging and selecting the combination of chiplets that you need to differentiate your product and run your workloads is a real enabler. And we're seeing that now expanding all the way into aerospace, similar things. But the point here is, in a software-defined environment, it's a natural fit into chiplets and 3D IC. That opens up this flexibility combination to many more companies and many more industries than just a large, monstrous SoC that takes up the entire reticle size. So it is an enabler. It is a democratization of this technology, and it's all going to be based on being software defined.
Yeah, I think it's been stated very well, but just to answer your question, yeah, it's a hardware problem. Standardization is going to be important to help identify how this ecosystem can get built out. It's also software because we're going to want the reuse in the software stack as much as possible on those different building blocks, and having that reuse over and over from generation to generation is going to be very important.
Yeah, just adding to the software point there that Matthew said. I mean, it's the end of the day, going back to the Sophie point that David made. So the whole idea of Sophie was to try and standardize some of the foundational level of software where there don't have to be any major differentiation. Example, boot flow, okay, or example, debug flow. So like we wanted to ensure that all ARM-based SoC implementations have up until some point, up until say CPU reset or whatever, have a consistent boot flow where the OEMs or the end partners don't have to sort of, go and keep changing that one generation over another generation. Debug, same thing. Security, same thing. So now when we were working together on the whole virtual platform initiative, we basically said, okay, we're going to enable this whole software defined vehicle infrastructure. At the same time, we will have to enable this standard software framework on top of that. So any differentiation that can happen on top of that is absolutely fine. But these are some foundational things that doesn't have to be mucked around, right? So that's where standardization becomes important because, as what Matthew said, it's just it enables a lot more reuse. It sort of, you don't have to differentiate where you don't have to differentiate. It's just, that's the whole idea of standardization.
I'm going to open this up to some Q&A from the audience. Should be a couple of mics here. Yeah. Please come up, ask your questions. If not, you'll have to listen to me ask questions, and I do this all day long for a living, so please.
Hello. About 10 years ago, I was working on an automotive system, and back then their design cycle was about 7 years. And our biggest fear was that somebody in Dearborn's going to cost reduce half our memory away. And so we were in a rush to fill up the memory first. I just wondered if the design cycle has changed. Has it gotten any better?
I can give you a concrete example. We may all have concrete examples. So one on the top of my mind is we worked with a German OEM a few years ago. I won't mention which one. And we were told you have a blank sheet of paper. You cannot talk to any of our suppliers. But if you were to use this methodology to define the next generation automotive platform, what would you do? We applied the methodology. We threw away several architectures within weeks. We had an architecture we decided on for both hardware and software. We implemented that. We created PCBs, enclosure, vibration, cooling, power analysis, thermal analysis, everything. And we had something on the road in 18 months. Significant reduction in time. And a small team. When the executives of that company found out we did in 17 months that they can barely do in 7 years with a very, very large team, well, let's just say we're still working with that company.
Yeah, it'll give you absolutely changing, definitely changing, and massively driven by China. It's just, I'll give you an example. Again, without naming the actual OEM, an OEM hired a silicon architect from Huawei in March 2023. I visited him in April 2023 just to say hi, greet him, make the connections. And he was embarking on their first generation ARM-based SoC for that OEM. Okay, they taped out in May 2024. 12 months, basically 12, 13 months. I did visit him again in July. He couldn't come to APM because his first silicon was expected last year. I visited him in July, and I was talking to him about, dude, like 14 months ago, you just came into this company. What did you do? he basically hired, I don't know, 375 people from wherever in China, okay? Got the hardware development done, and most of his software that he was eventually going to run was already running on pre-silicon environments on the chip. August, the chip powered on. October, they basically had the car, they had it in a prototype car running and testing. So again, 18 months, right? So again, this is not just one example in China. This is happening over and over again. We've been working with them very closely, with all of them. So we know that design cycle. Now, and I'll tell you one more thing, right? So there is this thing about, oh, China, it's going to bypass a bunch of, steps and stuff like that. My team has been working with them now for almost 2 years. And they all tell me there is no other OEM who asks more difficult safety, security, and mixed criticality questions than that particular team. So they do it. I mean, again, it's just, I'm not just boasting about China, but I'm just saying that is driving all the other regions to also think about the design cycles. Because if you really have to compete with that, you have to sort of change your processes, adopt things like virtual prototyping, adopt things like how are you going to do stuff in cloud, how are you going to move some of those validation in the cloud. So absolutely. So 7-year timeline, I think it's still there because we are in a transition right now in some places, but absolutely changing going forward.
Yeah, I visited that customer, and what I like to do, if they allow me, is I like to walk around through the cubicles and peek in and see what the engineers are actually doing. I was shocked. They were all running simulations. They were all having virtual hardware. They were developing the software. And then when I met with the CEO and the CTO, we were talking the same language. And the other part is what's different in China, and I don't want to get too far on that, but when I was at Qualcomm, I met with a lot of these handset developers in China. And they're looking at this as putting wheels on a smartphone. So in terms of the processes that they use, in terms of how they think about the problem, it's no different than what they've been doing. Okay, they just have these additional electromechanical things that tack onto it and everything else is fine. So they've already adopted these approaches and they're using them today with phenomenal results.
Yeah, and again, it's just, there are some areas which is astonishing. So the reason I visited him in July was to talk about the second generation, okay? And then my plan was, and that was my last meeting of the day at 2:30, 3 o'clock. And then I said, look, okay, we have to, his name is Mike, English name. And I basically said, hey, Mike, we'll talk about, the next generation. I'm heading back next week. Let's actually set up a Zoom call next week or the week after. He's like, what Zoom call? Why? So he said, who do you want? And then we went out, cubicles, 375 people, all under one roof. He picked up 5 people in the hall, took them to the conference room, and then he said, how much time you have? I said, you're my last meeting of the day. We sat for 2.5 hours, drafted the architecture for next generation. It's just that, right? I mean, it's not about cutting corners. It's not about anything else. It's not rocket science. It's about go, go, go. This is what we got to go, right? And this was last July. This October, they'll tape out the next generation, right? Double the performance of what the previous generation was. So, I mean, again, coming back to the point, yes, the development cycles are changing significantly. I believe to a large extent driven by Chinese timeline. But at the same time, I think, again, thinking about the whole, how AI is changing the whole thing, how, people have to sort of think about, you can't spend 7 years building one particular system that's going to be obsolete even before it comes to the market, right? So you have to basically pace up.
I think an interesting observation is that in the chip design world, we've been doing small CPUs. We thought they were really big back then. And then we'll put 4 of them on a chip. Wow, that's amazing. And now we've got 256 on a chip. And it's like, okay, well, that's, normal. And then we've got more caches, and then we've got AI engines. And, even our laptop chips have got maybe 30 to 40 CPUs in them that nobody even thinks about. They only think about the x86 core in there, right? There's all these other mini SoCs within there controlling power management and everything like that. So it's unbelievable system complexity in those parts, just in your laptop. It's insane. And what we're doing now is we're just taking that the next level and we're applying it to autonomous vehicles, software-defined vehicles, for example, data centers. How do we model an entire data center? It's what we've been doing the whole time. But we've just naturally thought, oh yeah, we're just going to model this a bit more and more, and our products have got bigger. Now we're just expanding that outside of the specific product into the entity that the software runs on. It used to be the single chip. Now it's a whole platform, a whole system. And so we're just naturally extending that methodology to that approach. And that creates these development cycles that are just, transformational. It's not going to take 7 years anymore. You do it in a year easily, right? It's just a complete game-changing way of looking at it.
Come on, Alex. Laptop chips also have ARM cores in it.
They do have ARM cores in it, it's true.
Okay. Thank our panelists. Did a great job. Thank you all for staying.